Good afternoon, all. I will start the session after 6, so let's wait so that people can join. Okay, all right, it's 6 o'clock. People can join in the middle also, so I'll start the session. I hope that I am audible. You can hear my voice clearly, and also my screen is visible. Uh, any one of you can confirm, please. You can use the chat box or you can unmute and speak. Okay, thank you for the confirmation. So I will start the session. So welcome to the live session for the course Introduction to Semiconductor Devices. So the course instructor for this course is Professor Norris Kumar Imani. He is from IT Hyderabad, and I will be the TA for this live session. I will conduct a live session on every Tuesday. You must have got the notification from the NPTEL team. My name is Ananya. I am a PhD student in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. So for this course, we will have 3 live sessions per week. I think you have already received the links for all of the live sessions. So the idea for this live sessions, maybe some of you have done NPTEL courses earlier also, so you already know how these live sessions are conducted. So idea for this live sessions is that we solve few questions, tell briefly about the topics that were discussed in the course for that week, and this will be useful for solving your assignments. And also, if you have any doubts in the course, you can ask. You can always use the discussion forum in the NPTEL website. So I will show you that also. Okay. If you have any doubt, you can go to this Q&A section and ask your doubts also, and you can clarify your doubts in the live sessions also. So I will conduct the sessions on Tuesday. You can join like all the live sessions as per your convenience. That is why, because this course number of students registered for this course is and the number is huge, so that is why the team is like arranging 3 live sessions in a week. You can join any one, or as per your convenience, more than one also. If you want to join all 3 sessions, you are welcome to join. You can join any of the sessions basically and clarify your doubts. So this is week 1. Usually how I do, like many times we solve my voice is audible, right? It's raining heavily, so if you face any like problem, then let me know. Okay, so normally how I start my sessions, I start with the topics those were discussed for that particular week, and then we'll go to the questions. Okay, you must have watched all the videos of this week for the week 1, but I will still go through all the topics very quickly so that everybody is in the same page. Okay, that will be helpful for all of you. So in the first few videos for this week, what we have learned, what are the different types of material, and the classification is according to like what we need in this course. Okay, so we have learned about 3 different types of materials: semiconductors, metals, and insulators. Okay, so how we classify all these materials based on their conductivity. Okay, so metals typically have very high conductivity, and typically metals have conductivity in the range 10 to the power 8 Siemens per meter, in this range. Of course, depending on the metal, that conductivity may vary, but the point is that metals have high conductivity. Okay? And then in case of insulators, insulators have very low conductivity. It can be in the range 10 to the power 12 to 10 to the power minus 20 Siemens per meter. So these are typical values. I'm not giving any like exact number. These are typical values of conductivity for metals and insulators. Okay. Now in semiconductors have intermediate conductivity in this range. Okay. Semiconductors have intermediate conductivity. Now, why this course is Introduction to Semiconductor Devices? Why semiconductors are useful for us? Because they have intermediate conductivity, and we can tune the conductivity based on our requirement. See, metals have very high conductivity, it always conducts. Insulators have very low conductivity, it does not conduct. What we want in our devices, we want controllability, and semiconductors give us that controllability. Okay, we can modify the current conduction and the amount of current based on our requirement, and that is why semiconductors are useful for us. Okay, there are various ways to change the conductivity of semiconductors that we will learn as we go through the this course. Okay, now what are the typical semiconductors that we are familiar with? Silicon, that is the most common one. Most of our devices, semiconductor devices, are made of silicon. Germanium, like people used to use this material earlier, but there are some problems with this kind semiconductor that maybe we will learn later. But this is another semiconductor. We don't use it very widely, like nowadays. Okay, and then another semiconductor that we use is gallium arsenide. Okay, gallium arsenide is a direct band gap semiconductor that you have already learned in the course in this week content. That was one topic, direct and indirect band gap semiconductor. And direct band gap semiconductors are useful for many optical applications. Okay, so these are the three common semiconductors that we are familiar with, and we will mostly talk about these materials, specifically silicon. Okay, so there are two types of semiconductors again. It can be elemental semiconductors. So sometimes I will write semiconductors as SC, don't get confused. Instead of writing the whole word, I might write sometimes semiconductors. Okay, SCs. And these are like single element semiconductors like silicon and germanium. And then we have compound semiconductors. It has two or more elements, okay, like gallium arsenide. Next discussion was on classical versus quantum mechanics. So nowadays for many of our devices we need the knowledge of quantum mechanics, although it's kind of like a different subject. So this course is not quantum mechanics, so the name of this course is not like quantum mechanics for semiconductors. So we will learn briefly about quantum mechanics because it is useful, but it is a vast subject. Okay, so we will touch this subject very briefly in this course. Okay, so we learned about classical versus quantum mechanics little bit. Okay, now why we need quantum mechanics? Classical mechanics is like Newton's law, and all these laws we are familiar with from our school life. Okay, everything falls in the classical mechanics category. Okay, classical mechanics is good for macroscopic work. That means particles, elements, not particles, like devices, or like for materials which are in macro dimensions, that is bigger in size. But classical mechanics sometimes fails when we go for very small dimensions, especially in the nanometer range. Okay, so classical mechanics is good for macroscopic work, okay, whereas we need quantum mechanics for microscopic elements, okay, microscopic particles like electrons, protons, any particles which has very small dimensions. So we need quantum mechanics for microscopic particles. Okay. Now what we do in quantum mechanics, we define something called a wave function. Okay, we assign a wave function to the microscopic particles. Okay. We assign a wave function and we denote it with psi. It is a function in space and also in time. We assign a wave function to quantum particles. What are quantum particles? The particles which have microscopic in size. Actually, we can assign this wave function to any particle, but we use quantum mechanics for microscopic particles. That is why we assign this wave function to quantum particles. Okay. Now, what is this psi xt? What is this wave function? It contains information about the microscopic particles or quantum particles. Contains information about the quantum particles and it is a solution of Schrödinger equation. So what it means that it contains information about quantum particles. As you know that by using mod psi square, so this gives the probability of finding a particle. So if we instead of so this is a function of x and t. Okay, we will ignore the time dependence part. If it is a function of space, that is x, we are considering only one dimension, so we have like this x direction, and we will try to find this mod psi square for a range of x, say x1 to x2, and we will find the probability of finding that quantum particle within this range. Okay, what is the probability of finding that particle between x1 and x2, and that we can find by taking mod psi square. Okay, that is why this psi contains information about the quantum particle. It contains informations like where the particle is present, what is the momentum of that particle, and other any measurable quantity, like for example what are the measurable quantities for a particle in macroscopic world. Say we have a ball, so position of the ball, say, that is one quantity. What is the weight of the ball, and if it is a moving particle, then we can calculate the momentum of the ball. So all these quantities are measurable quantities. So similarly we can measure this kind of quantities in quantum mechanics using the wave function. But since in microscopic world everything is a probability, so like even the position of a particle will be a probability. We can say that probability of finding a particle between x1 and x2 will be high, say for certain conditions, and probability of finding a particle in this region is say 0. Okay, we cannot define directly like where the particle is present. We can only assign a probability, and how we can do that using wave function. It is not very easy to understand. I'm just trying to give you an idea about classical versus quantum mechanics. Please go through the lecture videos for more understanding. Okay. Next, what we have learned, we have also learned about de Broglie's hypothesis, right, in the course. I don't know the exact pronunciation, like this pronunciation is a bit difficult because this name is, I don't know from which country, de Broglie's or de Broglie's, but just remember the formula and what is de Broglie's hypothesis. So what is this hypothesis? Says that this is about the dual nature of particle. Okay, so particles also exhibits wave-like behavior. And what is the wavelength associated with a particle? The formula is h by p. So h is Planck's constant, what is the value? Value is 6.62 into 10 to the power minus 34 joule second. So certain formulas you should remember, like this formula and the value of Planck's constant. We will use this Planck's constant value multiple times, like very frequently in this course. So you should remember this. Also remember the unit of this Planck's constant. So what is joule second? So joule we can write, if we write it in MKS unit, joule is kg meter square second to the power minus 2 and second. So the unit of Planck's constant is kg meter square second inverse. Okay, this is very useful while doing calculations, because that's how we will check whether our calculation is correct or not. And what is P? P is momentum. Okay. Momentum in classical mechanics, how momentum is noted, so that will be mass into velocity. Okay, so what will be the unit of momentum in classical mechanics? Say in quantum mechanics also the unit will be same. So mass is kg, velocity is meter per second. Okay, now if we take the ratio h by p, what will be the unit? This kg will get cancelled, second inverse will cancel, so only meter. Okay, so what should so meter is the unit of this wavelength. Okay, wavelength should have an unit as meter, right? So that is why the units are important in this course. So you have to be careful with the units and always check after doing some calculation. If there is a mismatch in units, then you will know that your calculation is not correct probably. Okay, so we have learned about these topics. I will take a pause. If you have any question, you can ask. You can use the chat box, or you can unmute yourself. You can also let me know if you don't need this brief overview of the topics, and if I can directly go to the questions and answers. I think this is useful, so that is why I am discussing a bit about the topics those were discussed, those were covered in the week. Okay. Wave function. Okay, I will discuss about Schrodinger equation and what it was discussed, what are the topics those were discussed in the class. So let's go to that. Now this wave function, it's a very abstract quantity. It is not easy to understand directly. So what I have mentioned earlier, that wave function is a solution of Schrodinger equation. Okay, what is the Schrodinger equation? It is a differential equation. I will write it here. So it is h bar square twice m del 2 del x2 plus vx and psi of x is equal to e psi of x. Okay, now this is time independent Schrodinger equation. I am only writing the space dependent part of the wave function. I am ignoring the time dependence part. I will not go into the details why I am ignoring the time dependence part. It's again, this is not a quantum mechanics course and cannot explain everything in the live session. If you are interested, you can read books, but we are mostly concerned about the space dependent part, that is the in the xyz direction, and for simplicity we are just taking only one direction, one dimensional case, that is our wave function is only in the say x direction, in x dimension. Okay, that means our particle can move only in x direction. Okay, so we will use so what is this Vx here? This is the potential the quantum particle is experiencing. Say if the quantum particle is inside of a lattice, say quantum particle, by quantum particle we mostly mean electrons. If the electron is inside a lattice, then it experiences the potential of each atom. Okay, you have learned that the potential of the atom looks like this. Okay, it concentrates near the nucleus. It has a kind of shape like this. So it can be this, it can be potential like we apply bias voltage. Okay, positive bias somewhere, negative bias somewhere. This potential can be anything, and this is a very general equation, and we solve this equation under various conditions. Okay, so the simplest case is solving this Schrodinger equation is for free particle. Okay, free electron. So first example was free electron. Now electron is a quantum particle. We assign a wave function psi to this particle and we will solve this Schrodinger equation. Okay, because the psi is a solution of the Schrodinger equation, and we will see how psi looks for a free particle. Okay, how we will do that? We will use the Schrodinger equation, time independent Schrodinger equation, and that will be minus h bar square twice m d2 psi. I am just writing d2, not this delta, because we are only considering our particle can move, particle is in x direction. We are considering only one dimensional case. Okay, so dx2 equal to E of psi, because our V of x is 0. Okay, for free particles mean our electron is not experiencing any potential, any bias or anything. Okay, it is free in the space. So this is a very ideal case. does not happen like this, but this is useful to understand many concepts. Okay, the example of free particle. So we can rewrite this equation like this: 1 by psi d2 psi dx2 is equal to 2m minus e by h bar square, and we write this whole thing as a minus k square. Okay, now this is like a second order differential equation, and the solution for second order differential equation we have learned in our school is that it can be exponential ikx, exponential minus ikx, or it can be sin x and cos x, and it can be combination of sin x and cos x also. Okay, now you can verify it, right? You can do second derivative and then 1 by psi. You can take this and you will get minus k square. You can take the secondary. This is an exercise for you. You can verify whether this solutions are whether this psi x are actual solutions of this Schrodinger equation or not. Okay, someone has written something. Is this a solution? How to check? You can check the double derivative. You can take this double derivative. Okay, so suppose you have exponential ikx. What is d psi by dx? Ik exponential ikx, that means ik psi x, right? d2 psi dx2 ik square psi x, right? So ik square will be minus 1 k square psi x. Now if we divide it with 1 by psi, you will get minus k square. So that means this satisfying this equation. That's how we check whether, even instead of this exponential ikx, if a complex expression is also given to you, how we will check? Take the double derivative 1 by psi, whether you are getting minus k square or not, or in this form or not. Okay, now we know that this expression satisfies our Schrodinger equation. So this is the wave function for a free particle. Okay, now what will be our energy? So from this expression we will write energy of our quantum particle, of our electron. Free electron is h bar square k square by twice m. Someone is on unmute. If you have any question you can ask, otherwise please mute yourself. So this is energy expression, h bar square k square by twice m. Okay, so energy is like a measurable quantity for a particle. Okay, so we got this expression, and why it is important? So this is known as the dispersion equation. Please mute yourself. Yeah, I will tell you. Just let me mute this person.
అసలు గ్రౌండ్కి వెళ్ళమాక నాని గోడవంత ఉండదు. సరే నాన్న గ్రౌండ్కి వెళ్ళమా
Actually, yes. What is k here? K is known as the wave vector. K is defined as 2 pi by lambda. Okay, I think you must have remember here. Professor told that another form of this is, so k is a very convenient term for us. So how we can write it? H by 2 pi and 2 pi by p. So that will be p is equal to h bar, and this will be 2 pi by lambda, and this is h bar k. Okay, so this k is wave vector, that is 2 pi by lambda. This is like a if you have watched a video, this is like a inverse Fourier transform. Okay, so this unit of this k is 2 pi by lambda, that is meter inverse. Okay, in real space we have units in meter, right? X, Y, Z direction in space. In Fourier transform, this is like an inverse of our space, that will have a inverse unit. So the unit of k is meter inverse. As of now, just remember this. Okay. This is our dispersion relation for free electron. We can take any values. So this h bar and m is constant for a free electron. H bar is already a constant, that is known as the reduced Planck's constant, and m is the mass of this electron, and k you can take like any value of k, and this relation will be satisfied. Okay, so dispersion relation, what it means, it is the relation between so in general, dispersion relation means the relation between frequency and wave vector. Okay, so energy, I'll not go into the details. Energy is related to frequency, and in case of like quantum mechanics, the dispersion relations mean the relation between energy and the wave vector. Okay, don't get confused. This is basically the relation between E and K. Okay, now this is our relation for free electron. Now we can find like you can do this exercise. I will not go through it into it. What I have mentioned, like mod psi square, this is the probability of finding an electron. Okay, now the particle has to exist somewhere. Okay, if you just, this is our x direction, if I check my particle from minus infinity to infinity and take mod psi square dx, this should give me 1. You can verify whether it gives 1. You can take mod psi as this value, this expression, and verify whether it gives 1 or not. This has to be satisfied, because if our particle exists in x space, then it has to be exist somewhere. So from, if we check from minus infinity to infinity, it should give us 1. That is the physical meaning of this mod psi square. Okay, even though this quantity is a very abstract quantity, this gives us some information. Okay, next, what example we have taken, I will just briefly tell it, because we will not have much time for questions. The example 2, I will write it with a different. our example 2 in the course was electron in a infinite potential world. Okay, this is our example 2. So inside this potential, inside this well, Vx is equal to 0, and outside, this is infinite. Okay, and this is a finite potential well that we will discuss later. So what is the wave function for this finite potential well, infinite potential well? Inside the well, the wave function is a sine kx plus b cos kx. How we can get this expression? Again from Schrödinger equation, and we can use call log. I didn't understand what you are saying. What do you mean by call log? Please clarify what you are asking. I'm not getting what you mean by call log. Okay, so this is the wave function for electron in infinite potential well, and this is in between this well. Okay, not outside the well. Outside the well, the wave function is 0 because the this potential is infinite. Electron cannot jump from this well to outside. Okay, so this is our wave function, and what we have learned in the course is that in this case our energy values is quantized. Okay, h bar square kn square 2n. This is the dispersion relation. Mid display. Okay, I will try to make it small. I'm trying to make it as small as possible. Okay, this actually, if I keep this call log, then I can be in the presentation mode and see if someone is commenting or something like that. That is why I'm keeping it. I will hide this one too. This is not necessary. I will go into that. And this is equal to h bar square by twice m, and k's are quantized, so we know that this is n square pi square by l square. Okay, how we can get this was discussed in the class. I'm just giving you the expression. So the key idea here is that energies are quantized. So what quantum mechanics tells us, as soon as we confine a quantum particle somewhere, the energies gets quantized, the wave vectors gets quantized. And why this is important? Because of this we actually get, so we'll talk about this. This is how we actually get band gap in our materials. Okay, now instead of infinite potential well, if we have a finite potential well, we have another phenomena that is known as the tunneling of electron. You can see the wave functions are a bit outside, so the wave functions are not 0 exactly, but wave function decays. Okay, the probability of finding the electron decreases outside this well. The potential is 0, so electron is not experiencing any force inside this well, so the probability that the electron will be inside the well, that is higher. That is very like, we can say this like that without even knowing quantum mechanics, right? There is no force on the electron, so there is a probability that the electron will be here most of the time. Okay, we'll find the electron here. So the probability of finding the electron inside the well is high, it decreases outside the well. Okay. Now the key idea is that instead of infinite potential well, here everything we are trying in one dimension. Even if we go for higher dimensions, say in 3D, in case of atoms, the electrons energies are quantized. Electrons are confined within, like nearby the nucleus within the atom, and that is why quantum mechanics was able to explain many of the topics. Because, please mute yourself, otherwise I have to keep everyone on mute. I kept everyone on mute because it was creating a disturbance. If you want to say something, you can just write in the chat box, or if you want me to unmute you, then just tell me. Okay, write in the chat box. Okay, so what I was saying is that instead of a potential well, we can think of an atom, a 3D electrons in an atom, that is in a 3D scenario, and electron is confined. Okay, so earlier what was the question is that even though there is a nucleus, an electron is obviously attracted to the nucleus because nucleus is positive. How electrons are actually moving near the nucleus? It is not why it is not falling into the nucleus, and quantum mechanics was able to answer these questions because electrons are moving in a particular, because energy levels are quantized. Electron is at a particular energy level and it has a particular wave function. It actually fits in within that in the radius that in the circle that it is moving, and it is not falling into the nucleus. Okay, that's why that's how quantum mechanics explain many of the things classical mechanics was unable to describe. Okay, we can solve this Schrodinger equation in case of atoms, and we can find the energy levels of electrons inside the atoms. Okay, that is a complicated problem. Only we can solve these kind of problems like free electron and electron in infinite potential well or finite potential well analytically in pen and paper. Okay, we can solve the problem for hydrogen atom because it has like only one electron, but that is again a very complicated problem. It's not like we cannot solve it. We can use Schrodinger equation and wave function concept to solve the electron energy levels in any scenarios basically. Okay, so that is how we know that atoms, electrons in atoms have particular energy levels. Okay, now what happens when there are many atoms. Okay, and how the band gap is generated. Here we will learn about this chronic penny model, and this model explains how band gap is generated in a crystal structure. Okay, we have learned about Schrodinger equation, we have learned about free electron and how it behaves. We learned that when the electron is confined in a well or in any kind of potential, it experiences any potential, then energy levels get quantized. Now how the electrons behave in a crystal structure and how band structure is generated, how the band gap is generated. Okay, before going to that, I will briefly discuss about silicon because this was discussed in the class. So this is the crystal structure of silicon. It has a diamond structure. That means it is a face centered cube. You can see this is a cube and this is face centered, means there are 8 atoms at the edges and there are atoms at each face, and there are 4 atoms inside of this cube. Okay, this kind of structure is known as the diamond structure, and silicon has this diamond lattice structure. The lattice constant, that is the distance between these 2 atoms, generally denoted as A, and for silicon this is 5.43 angstrom. Okay, this is for silicon. So these are some values you have to remember for some calculations. Okay, most of the time these values will be given, but it's good to know, like at least for silicon you should remember these values. And density of silicon, we can again calculate it, we will calculate it in the course, is 5 into 10 to the power 22 atoms per centimeter cube. So if it is a centimeter cube volume, then there will be 5 into 10 to the power 22 atoms of silicon. That's a lot, right? And this quantity is important when we will talk about doping. Okay, in 1 centimeter cube there is 5 into 10 to the power 22 atoms of silicon. If we if we add another type of atom in silicon lattice, that is known as doping, and that will give us, say the doping is 10 to the power 16. You can see that 16 dopant atoms per centimeter cube. So you can see this is 22, this is 16. So this number is actually very less compared to silicon. Okay, that's how actually we will say whether our material, whether our silicon is lightly doped or highly doped. All these concepts will come. We will discuss about this later. Let's focus on chronic penny model. So what chronic penny model, it is a very simplified version to explain a band diagram. Actually the practical scenario is much more complex than this. So what chronic penny model says, so atoms have this kind of a potential, and if it is in a lattice, then there will be many of these atoms, there will be this kind of potential. Okay, we are just considering one-dimensional lattice. That means our atoms are arranged, so this is the nucleus of our atom. Okay, these are arranged in one dimension with a certain gap, say A. Instead of this kind of a potential, because we have to write a potential as a Vx function, right, for Schrödinger equation, this is very difficult. So what we do, what this model does, it simplifies with a square potential like this. This is a very like simplification of the atomic potential. Okay, so if this is the potential, this is V naught. Again this is similar to the finite potential well kind of scenario, kind of inverse. Okay, there will be this region where it will experience outside of it, it will experience V naught potential, inside it will be 0, something like that. Okay, now this is the simplification of this atomic potential in one-dimensional lattice in this KP model. Again what we do, we solve Schrödinger equation, and this is not a complex mathematics, actually it involves multiple steps. You can try at yourself, but if we solve Schrödinger equation, I will not solve it, but I have done this in my coursework while doing coursework in my PhD. It is not complicated. I'll just give you the idea, like if we solve it, what we actually get. Okay, if we solve Schrödinger equation, for this potential, for this Vx, okay, and we do some mathematics, some simplification. If you have any doubt, you can ask me, because these are like not a very straightforward. We get an equation like this. I'll just give you a very simplified version of the equation. This is a very long equation. Okay, it is the equation which is a function of energy of the electron. Say there is an electron here somewhere, I don't know, the energy of that electron, and it has a expression like, in the right hand side, cos ka. This k is the wave vector, you already know this, and a is this interatomic distance, okay, or the lattice constant. We get an equation like this. If you are interested, you can do the mathematics, you can solve this Schrodinger equation. We finally get an equation like this. This equation is given in the Niemann book, that is the textbook we are following for this course. Okay. Now what happens, I'll go to the next slide. Okay, this I have taken from the book. So we have this expression, function, some expression in terms of energy is equal to cos ka. What we can do, we can plot this for different E, right? Our expression is function of energy is equal to cos of ka. KP models explain how we get band gap. Okay, that is what I am going to explain. So we can take any values of E, energy, and fit that value in the left hand side of this equation. We can find what is the corresponding number, like what is the left hand side value. Okay, and if we plot that value, and if say this will come, my drawing is not very good, but this will come something like this. Okay, I will make two lines here. This is +1, this is -1. So this is our left hand side of this equation. Now what this expression says, this left hand side should be equal to right hand side, right? What is right hand side? Right hand side is cos ka. We know that cos, it should be within ±1. Okay, cos value should not exceed +1 or -1, right? That we know from our school mathematics. What we observed here, some values of this left hand side, say in this portion, actually is above this +1. This portion is actually below this -1, this portion. But that is not possible, right? Cos value should be in between +-1. So these values, these corresponding energy values are not permitted. That means we have a band gap here. Electron cannot take the energy values in this range. Okay. Now if we plot it like using some tool, we will know that this point is our +π/a. Okay, and you can check the book values in the book. I don't have all the values. Okay, now in this range we don't have any band. any allowed energies that an electron can take. Now instead of this graph, we can have a graph like this. So these are the k value, k equal to, so we can plot, instead of this energy, we can plot k in this axis and E in this axis. Okay, wherever you see these gaps are actually these portions. Okay, this graph is and this graph is similar, only difference is that we are drawing it in E versus K as per the dispersion relation. Okay, so we have drawn this graph from this graph, and now again we can simplify this graph to again by in reduced K zone. We can shift everything by 2 pi, because cos 2 pi plus Ka will be same as cos Ka. So that's how we get this kind of graph. Now here, so this axis is energy, right? These energy values are forbidden, so these are not allowed. Remember when we tried one-dimensional infinite potential well, there we have like a one single energy level, then again a jump, another energy level. Here we have like small energy level, like many energy levels in this range. Okay, and no energy level here, and again energy levels here. Now this similar kind of diagram will be, so this is in K space. If we draw this in say position, say X, we will get something like this. Above this will be allowed, below this is allowed, in this region not allowed. Now if we call this as a EC, edge of conduction band, and if we call this edge as EV, valence band, this is our band gap EZ. Okay, this is energy and this is position, say X, and we cannot have electrons in this range. We have all the electrons in the valence band if it is at 0 Kelvin, and if there is some electrons are excited with some energy, then electrons will move from valence band to conduction band. It will not stay here because there is no space for electrons to stay here. It cannot take energy in this range. It will directly go to the conduction band if it has enough energy, and these are not allowed. Okay, so that's how you can see that using Schrodinger equation, from this simplification we can finally get this energy band diagram that we are familiar with. At least we are familiar with for silicon. Okay, so this EZ for silicon is 1.12 electron volt at a certain temperature, that is at room temperature 300 Kelvin. It can take a different value. Okay, but this is the origin of having a band gap in a semiconductor. If you have any doubt, I will take a pause here. These topics were discussed. I'm just discussing again for clarification. Okay. Now this is how band gap arises in case of crystalline material. Another way to visualize how band gap forms, we know that in case of atoms, it's like a 3D version of this infinite potential well or finite potential well, right? So it will have discrete energy levels like this. What we already know, another thing is that as per Pauli's exclusion principle, no two electrons can have same energy levels. Now suppose we have an atom here, this will be the nucleus, and another atom here, this will be the nucleus. These are far away, they are not interacting. Their potential of this atom, which has this kind of a shape and this has this kind of a shape, they are not interacting. Okay, there is one electron say here, one electron say here, and it has an energy level E1, it is in the energy level say U1. Now as they are not interacting, this E1 and this E1 can be same. But if the atoms are closed by, their potentials are actually interacting, then these two electrons cannot have same energy level. As per Pauli's exclusion principle, it will have say some E1, it will have some E2, and there will be a delta E difference. Now this delta E difference will depend upon like how close these two atoms are. Okay, now we have, instead of a one energy level, we have two energy levels. If we have two energy levels for two electrons, those are in two atoms. Now what will happen if we have n numbers of atoms and n numbers of electrons? Then we will have how many energy levels? We'll have n energy levels, right? E1, E2 up to En, right? Something like this happens when we form a solid from atoms. Okay, so we have this discrete energy levels E1, E2, E3. This is like one energy level, but in atoms we will have E1 and E2, E3. Okay, electron will occupy the lowest energy level because it tries to minimize its energy, right? So we can have multiple energy levels. So say these are different energy levels. Okay, and say electrons are here. Now we are taking those atoms closer to each other. So what will happen? The energy band will start to split like this. This diagram you have already seen. Okay, instead of one energy level, we'll have multiple energy levels. So this is the energy axis, right? Now the outermost cell or the outer energy levels will split first, because they will interact first. Say we are decreasing our distance, so this is the interatomic distance. Okay, as we are decreasing our interatomic distance, the outer energy levels will interact, they will split first. The next energy level, the inner energy levels, will interact a bit later, they will split later, and the innermost energy levels will split even later. Okay, if we really keep those atoms very close. Now normally what happens, we will have a position which is like x naught or a, whatever like notation we use. This will be like a stable position for that elements, for those atoms. Okay, so this is the interatomic distance or lattice constant for solids. Okay, at this point the atom, the crystal structure of this atom will be stable. So that means the innermost energy levels of the atoms are not splitted, they still have the same energy values, but because they are not interacting, so we don't care. Only the outermost cells electrons, only the outer electrons will have this kind of a splitting. That is why we are mostly concerned with the valence electron, that is the electrons in the outermost cell. Okay, so we have learned about silicon, how this splitting happens in silicon. So if it is energy and this is the distance x, so electrons will have this kind of a structure. So this, in case of silicon, so this is for silicon, this is 3s and this is 3p states, orbitals. So it has total, if there are n number of atoms, then it has 2n states, 2n electrons, and it will have 3p orbitals have 6n states, but it has 2n electrons. Okay, all the levels are not full. As we keep it closer, then the energy levels split like this. The diagram is not very good, but you can refer to the textbook. Okay, so there will be total, there are 8 n states, so there will be 4 n states here in the upper band. Actually there are many levels here. Okay, like this, and there will be 4 n states here, and these are all, everything will be filled in this range. This is our conduction band and this is our valence band, and there will be 4 n electrons, and these are empty. Okay, somewhere in this distance, a naught or a, I will denote it, this is our lattice constant, and say our silicon crystal structure, which is a diamond structure, as we have discussed, is more stable for this distance. Okay, what is the value of A for silicon? 5.43 angstrom. So this is energy axis, so this is our band gap, easy. This is our conduction band, this is our valence band. Valence band is completely filled with 4n electrons if there are n number of silicon atoms, and conduction band is completely empty with 4n states. All the states are empty. This is true when the silicon lattice is at 0 Kelvin. Okay, otherwise some of the electrons from valence band will go to the conduction band because of the thermal energy. Now as you can see here, this value, if if we increase this distance, the interatomic distance a bit, this gap decreases. If we increase the interatomic distance, this gap actually increases. Okay, that is why even though we say that silicon has a band gap of 1.12 electron volt, this is not exactly correct. Okay, this is correct only at 300 Kelvin. Okay, now if we apply a lot of in lattice point, yeah, this is the lattice, this is the stable position of the lattice. Okay, we have a crystal structure, the distance between two silicon atom is a, there is a splitting, that is why we get band gap in case of silicon. Okay, in the stable position we get a splitting at the outermost valence shell. Okay, not the inner ones, as you can see. Okay, so if we change the lattice structure, distance between the silicon atoms somehow, say we are applying a lot of stress, we are actually decreasing the distance between two silicons, then we will actually increase the band gap. And sometimes what may happen, if we apply a lot of heat, say the material actually expands because of the heat, so interatomic distance will increase. In that case, the band gap will actually decrease. Okay, so you should remember this graph. This graph what I have drawn is not very good. You can refer to the book, you can refer to the lecture note. It was given there also. The last topic that was discussed, I think I'm taking quite a lot of time, but I hope that it is useful. You can tell me in the chat box, you can give me the feedback also, whether I should include this discussion before going for to the question and answer or not. Next, what we discussed about direct and indirect band gap semiconductor. So what are direct and indirect band gap semiconductors? That we get from this EK diagram. Okay, this kind of a diagram. So there are many energy levels here. We will focus on only conduction band and valence band. What is conduction band? The band where, so this is one energy band. There are many small energy levels here, so we call it as a band. Okay, this is another band, this is another band. What is the valence band? Valence band should be completely filled with electrons. Okay, that is the lowest level, that is completely filled. Say we have a valence band in K space like this. In real materials, the band structure can be like a very weird, okay, not exactly like this kind of a shape. Say this is a valence band and this is completely filled with electrons. We will call it as a valence band because it is completely filled. And what we call it as a conduction band, this is the lowest energy level which is not filled. This is our conduction band and this is our valence band. That's how we define valence and conduction bands. Okay, why we call this is our valence band? Because this is filled and this is empty at 0 Kelvin. That's why we are calling it as a conduction band and this is a valence band. Now in case of direct band gap semiconductors, we will look at the EK diagram. In case of, so this is conduction band and this is valence band. So the maxima of the valence band and minima of, okay, I have written it opposite, so this is conduction band. The maxima of the valence band and minima of the conduction band is at the same K position, then it is a direct band gap semiconductor. EK, this is my valence band, say, and this is my conduction band. The maxima of the valence band and minima of the conduction band is not at the same K position. We call it as an indirect band gap semiconductor. Now why we need this classification? In case of direct band gap semiconductor, when an electron moves from conduction band, say due to some excitation, some optical absorption, an electron moves from valence band to conduction band. Okay, when the electron will come back from the conduction band to valence band, then what will happen? It was at a higher energy, it will come at towards a lower energy, so it will release its extra energy. Okay, how it will release its extra energy? In form of a photon, in form of light. Okay, because there is not change in K. Okay, what is K? What is P actually? H bar K. And P is basically momentum. In classical mechanics, it is mass into velocity. In case of photon, it's a massless quantity, so it has momentum, but this value is very small. The change in K is very small, and that is why it releases as a photon. In case of indirect band gap, when electron moves from conduction band to valence band, it will move from here to here because there is no state here. So there should be a change in K, and that change in K will be satisfied by phonon. Just remember this term. Cannot explain go into the details. this change in K cannot be satisfied by photon, because photon has a very small change in K. It's a massless quantity. The calculation you might have remembered, right? For photon, the change in K is very less. That is why if it is only a direct bandgap semiconductor, this photon emission can happen. In case of indirect bandgap semiconductor, phonon emission happens. Photon is light. Phonon is basically heat. Okay, so in case of indirect bandgap semiconductor, instead of giving light, it generates actually heat. The material gets heat up. Okay, that is why when we want to use a semiconductor for optical applications, for like LEDs and laser, we will use a direct bandgap semiconductor, so that when the electron moves from conduction band to valence band, it will give us a photon. It will give us a light instead of heat. I think someone has asked about electron hole pair generation. It's again from this diagram we can see, like whenever, so this is a certain energy. So electron can move from valence band to conduction band, or from any energy level to higher energy level. It can, if it gets enough energy, right? For moving an electron from here to here, you will need this Eg amount of energy, right? So if our energy can be in form of optical absorption, we can apply a laser, we can apply a lot of heat. Energy can have any form, right? If we apply enough energy that is equal to or more than EV, then an electron can move from valence band to conduction band. And when it moves from valence band to conduction band, now electron is in conduction band. That means the electron is free. We have a free spot here. That energy level in the valence band is empty. So this is known as the holes. Okay, that is how electron and hole pair generation, if we apply enough energy higher than the band gap of the material. Okay. If the band gap of the material, if the energy applied is not enough, that it cannot excite an electron from valence band to conduction band, then that energy will pass through this material. It cannot create an electron hole pair. Okay. I hope it is clear. I don't know how much time I took. Okay, we have maybe like 40 minutes. I will solve few questions. Please tell me whether this discussion is useful or not. Otherwise, from the next class onwards, I will directly go to the questions or very briefly describe about the topics. Okay. Okay, so yeah, I will try to take less time, give okay, thank you. So let's go to the questions then. Some of the questions, may, if you have attended the earlier live session, some of the questions will be similar, so you can do along with me. Okay, so the first question is, calculate the first 3 energy levels of an electron in an infinite potential well of with L equal to 1 nanometer. So this question was asked in the class also. So I'm giving the same question. So this is the infinite potential well, Vx, this is infinite, this is x direction, say this is 0 and this is L. My electron is inside the, okay, I cannot say electron is inside a well exactly because it's a quantum particle, but because it's an infinite potential well, so electron cannot go jump from this well to outside, so I can say that the electron is inside a potential well. So this is reason 1, this is reason 2, and this is reason 3. And if we use Schrodinger equation, we will know that our electron will be here. It will have a wave function psi of x, okay, that is like a sin kx plus b cos kx if x is between 0 to L, and it is 0 if x is less than 0 or x is greater than L. Okay. So I will give you some time to solve this question. You can tell me the answer, the values E1. We know that this energy levels are quantized, right? So this expression I will give you, h bar square n square pi square by 2m L square, okay, and I want to know E1, E2 and E3 values in unit of electron volt. I hope that you are doing the calculations. If you are done, you can tell me the answer in the chat box. Point 36. For first level, yeah. Okay, let's check. So here, what is h bar? So h bar is reduced Planck's constant. H is Planck's constant. H bar is known as the reduced Planck's constant. What is the value? So h is 6.62 into 10 to the power minus 34 joule per second is divided by 2 pi, and this value you can calculate 1.054 into 10 to the power minus 34 joule second. Again, units are important. you have to pay attention to it. N will be 1, 2 or 3 because we are considering only first three energy levels. Pi we know. M we are taking the mass of free electron, that is 9.1 into 10 to the power minus 31 kg. Okay, let me write this in terms of MKS unit also. 1.054 into 10 to the power minus 34 kg meter square joule inverse. Okay, and our L is 1 nanometer, that is 10 to the power minus 9 meter. You see, I have kept everything as in this unit so that I don't make any mistake while doing conversion. Okay, now this expression E of n, let me write like this: n square h bar square pi square by 2m L square. Okay. Now if n is equal to 1, then this expression is E of 1 square is 1, so this is h bar square pi square by 2m L square. And if instead of n 1 we have any other value of n, this will be like n square into E1, right? This is E1. So I will only calculate E1 and then multiply with n square. So what is my E1? It will be h bar square, that is 1.054 into 10 to the power minus 34 square pi square divided by 2 into 9.1 10 to the power minus 31 into 10 to the power minus 9 square. Let's check the unit. What is the unit of energy? It can be either joule or it can be either electron volt, right? So our unit is, this is kg meter square second to the power minus 1. This is whole square actually, so this is 4 minus 2. Okay. This is the unit of h bar square. Pi is unitless. This is kg meter square. So what we have in unit? Kg meter square second to the power minus 2. This is actually joule if you write joule in MKS unit. So this we are getting the answer in terms of joule. Okay, 10 to the power minus 30. Okay, yeah, that is in joule. So when you tell me the answer, you should also mention the unit. Okay, so if you calculate this will be I have done the calculation earlier, 6.02 into 10 to the power minus 20 joule. Now to convert it into electron volt, what I will do, I will divide it with Q, 1.6 into 10 to the power minus 19. So that will give me 0.37 around electron volt. So this is my E1. What will be my, so my E1 is 0.37 electron volt. E2 will be n square into E1, so 4 into 0.37, that will be around 1.5 EV, and E3 will be 9 into 0.37, that will be around 3.38 EV. Okay, you just need to calculate E1 correctly, and rest of the energy levels you can calculate using this expression. En is n square into E1. Okay. Yeah, and be very careful with the units. Let me give you the next question. If you have attended, I don't know, maybe the other TAs also have discussed this question, but I will give you the question anyway, and this time you can tell me the answer. Okay. The wave function of a particle moving in free space is given by psi is equal to exponential ikx plus 4 exponential minus ikx. The energy of the particle is what? There are few options. A is equal to 3h bar square k square by twice m. B h bar square k square by twice m. C h bar square k square by m. And D 5 h bar square k square by twice m. So this is very simple. We have already discussed. You can tell me the answer in the chat box. Should be yes, you are correct, whoever has given the answer. The wave function is in exponential form and the particle is moving in free space. That means it is the wave function of a free particle, and we already know what is the energy of free particle. So that is h bar square k square by twice m. And how we get this? Again, we get this from Schrodinger equation. Del 2 psi del x2 is equal to minus of 2m h bar square e 1 by psi. Okay. Again, you can try this side, find this expression and see whether you are getting this minus k square as answer or not. this is for which kind of a well? So this is for free space. This is not for well. So that means the particle is not experiencing any potential, and our V of x is equal to 0 in this case. That is why our time independent Schrodinger equation has this kind of a form. Okay. This is a very simplistic equation. Ideally we don't have like a free electron moving outside, right? But this is a very important expression. So this the answer is already given for this question. We already know that the density of silicon is 5 into 10 to the power 22 atoms per second. So this is the correct answer. But we will see how we get this. Okay. So the question is, silicon has a diamond cubic lattice structure. So this is the lattice structure. I have shown you earlier this structure also. So there are 8 silicon atoms at the edges. There are atoms at the 6 faces, and there are 4 atoms inside. This is like one FCC crystal structure, if you are aware of crystal lattice. So if this is a cubic structure, there are 8 atoms like this, and one atom on each side, each face of this cube. Okay, so there are 6 atoms on the faces of this cube and 8 atoms at the edges. So this is known as a FCC crystal structure, face center cubic. So this is a cube, and there are atoms at the faces. That's why this is a FCC lattice. What is a diamond lattice? 2 FCC lattice. Okay. One of the FCC lattice is translated 1/4 diagonally. Okay. Just visualize it like this. We have 2 FCC lattice. Say it overlaps. Now move one diagonally by 1/4 of lattice constant. That means a by 4. Okay. And if we do that, and if we only draw this one FCC, there will be 4 other atoms from this second FCC lattice that will be inside this first FCC, this cube, okay, in this structure. So that is known as the diamond structure. Okay, so silicon has this kind of a structure. Many semiconductors have this kind of a structure. And in case of silicon, this A is 5.43 angstrom. We have discussed. These are few constants, so these numbers will be given in like if you are going for an exam or something, but it's always good to know, good to remember at least the values for silicon. Okay, 5.43 angstrom. The silicon crystal is formed by periodic repetition of unit in XYZ direction. Silicon is a crystalline material. It was discussed in the class what are crystalline material, what are amorphous material, what are polycrystalline material. In crystalline materials, the atoms are arranged in a particular order. For example, in case of silicon, it is ordered in a diamond cubic structure. This structure will be repeated in 3 dimensions in X, Y and Z to get the whole block of silicon. Okay. In each unit cell, there are 8 atoms at the corners, as I have discussed. It is shared with 8 adjacent cells. So there will be, if this is one unit cell, there will be 8 adjacent cells, okay, in different directions in 3D. So this edge corner atoms will be shared by 8 adjacent cells. Hence the corner atoms are considered to contribute 1/8 of the unit cell, okay. Effectively, even though there are 8 atoms at the corner, we are actually having 1/8 into 8, that means 1 atom of corner atom inside a cell, okay. There are 6 atoms in center of each face. This is shared by 2 adjacent unit cells. For example, say this is one face atom. This will be shared by this unit cell and the cell that is in the side of this, okay. So effectively, how many face atoms we will have? So half portion of this atom will be within this one cell, right? So this is like half, and there are 6 in total face atoms. There are 6 faces in a cube, right? So this is 3 atoms. Lastly, the 4 atoms within the body of the unit cell that contributes fully. So these 4 atoms, these are completely inside of this cell. That is coming from the second FCC lattice, but it is inside of this one unit cell. So they contribute fully. So the effective number of atoms in one unit cell is this 1/8 into 8 equal to 1. This portion, half into 6 and 4 into 1. 1 because they contribute fully, and there are 4 full atoms. So there are total 8 atoms inside one cell of a diamond cube lattice structure of silicon. Now we have to determine the density of atom. How many number of atoms are there per centimeter cube of a silicon block, say, okay. So density is number of atoms per unit volume. We determine everything in terms of centimeter cube in most semiconductors. So how we will do that? We know that the interatomic distance is 5.43 angstrom, which is angstrom is 10 to the power minus 10 meter, okay. So I will write it in terms of nanometer, 0.543 nanometer. Number of atoms in one unit cell is 8. This 8. Now volume of this unit cell is so it is a cube. What is the volume of a cube? A cube, right? This is a cube. All 3 sides are equal. So the volume is A cube. So that is 0.543 into 10 to the power minus in nanometer. I will write it in terms of centimeter because ultimately we will need the density in terms of centimeter. So that will be 10 to the power minus 7. It's a centimeter whole cube. So this will be, quickly do this. (1.6) into 10 to the power minus 22 centimeter cube. You also do this calculation along with me, then it will be helpful for you. How we will calculate density? Number of atoms per unit volume. So we know that there are 8 atoms inside a unit cell, and the volume of this unit cell is 1.6 into 10 to the power minus 22. So the unit is atoms per centimeter cube. Do this calculation and see whether we get 5 into 10 to the power 22 or not. We exactly get 5 into 10 to the power 22, which is the density of silicon. Now say instead of a silicon atom, if we have another type of lattice, another like different lattice constant, then also you will be able to calculate the density for that material, right? How you will do? You will determine the effective contribution of each atom to the unit cell, and you will calculate the number of atoms inside one unit cell like this formula. Okay, it can be different. For example, if it is a FCC lattice, face centered cubic, then it will have 1 plus 3. We will not have this 4 extra atoms inside this unit cell, so we'll have like 4 atoms, and then again we can calculate the volume of this unit cell. Okay, since this is a cubic unit cell, so our volume is AQ. If it is not cubic, say the dimensions are not AAA, instead of say ABC, then you can also calculate the volume. Okay, A into B into C, and then you can calculate the density of atom. This is the process how we actually calculate the density of atoms in any solid. Okay. Let's go to the next question. We have time for 1 or 2 questions, so let me give you this. Consider 2 semiconductor materials germanium with a energy band gap of, what is the energy band gap of germanium? 0.7 eV. And sapphire, you know what is sapphire? Sapphire is basically Al2O3, aluminum oxide. With an energy band gap of 9.9 eV. Which material will be transparent for visible light? Of wavelength lambda is equal to 400 nanometer. Okay. This question is again on absorption. So you already know how to solve this. So we have some energy levels E1, E2 or EC, EV. Okay, electron will jump from here to here, and if an electron can jump from here to here, if the energy is enough, then that energy will be absorbed by the material. If that energy is not enough, then the energy will pass through this material. Okay, then the material will be transparent. So the wavelength is given. We will first calculate the corresponding energy. So lambda is 400 nanometer. So we'll calculate energy. Light pass through it. Yeah. Sapphire will be transparent here. So energy of this corresponding photon will be the formula is Hc by lambda for photon. So if you multiply these two, you will get 1.24 by lambda if we write lambda in micrometer. So or if you write in like in nanometer, this will be 1240 lambda, that is in nanometer. Okay, not here, so this is here, the micrometer, and we will get the expression in EV, energy in EV terms. You can do this calculation. You can multiply C, H and C, and you can convert it to electron volt, because that will give you in joule. You can convert it to electron volt and see whether you get this 1.24 or 1240 number or not. Okay, so I'm just directly giving you this expression. So 1240 by 400, because our lambda is given in nanometer, so this will be 1240 divided by 400. This is 3.1 electron volt. Now if our energy of photon is higher than energy band gap, then what will happen? Absorption will happen. Electron will go from EV to EC, I mean valence band to conduction band. Okay, if our energy of photon is less than EC, then this photon will transmit through this material. It will not get absorbed. No electron hole pair will be generated, and the material will be transparent, right? In our case, EZ of germanium is 0.7 EV. So which condition is satisfied? This condition, right? So absorption will happen. In case of sapphire, I'll write Al2O3. Transmission will happen. Right? So our sapphire is transparent to visible wavelength. So I actually have few more questions, but we already have time, so it's 7:58. We will discuss about the other questions in the next week. Still have 1 or 2 minute time. If you have any doubt, you can ask. Otherwise I will stop the session here. I hope that the session was useful for you. Infinite uncertainty product. Okay. You are calculating del cross h bar. See what the uncertainty principle says. Del cross h bar is greater than this h bar by 2. Okay. So there is not equal sign, it's greater than or equal. So if you are getting that condition, then it is correct. Okay, I have to calculate the del cross h and del cross del x and del p values for finite potential well. I have not done it earlier, but see that h cross by 2, that value is like, that is very small values, like h is 10 to the power minus 34 in terms, right? That uncertainty is very small. So if you are doing some mistake, like some calculation mistake or something, then it may not be satisfied, but explanation is greater than or equal to, right? So it still holds correct, it should hold correct. Okay. I will try to check it also and let you know in the next session. Yeah, every week the meeting code will be same, at least the session that I am taking, and I will upload the slides. The NPTEL team will share it with you. So I don't have the access to share with you directly. The NPTEL team will do that. You will get notification for that. Probably you will get that in here. There will be another section for this live discussions, and there you will get the all the slides. Okay. Please wait till the NPTEL team inform you. Repeat the timetable. So the live sessions are, it was given so there will be 3 live sessions in a week. I will take the Tuesday one. The code will be same. If there is any changes with the schedule or with the meeting code, then you will be notified earlier. Okay, you must have got this notification for today's session one day before. Yesterday you must have got the mail. Similarly, you will be informed before every session. If there is any change also, you will be informed before the session. Okay, so if there is no more question, then let's stop the session here. So thank you everyone for attending the session. I hope that the session was useful, and see you in the next session.